Hello everyone, and thank you for tuning in once again to the Group 3 podcast. This is the show where we talk to working mathematicians about what it's like to do research for a living. My name is Logan, and today we are joined by Dr. Matthew Satriano, assistant professor here at the University of Waterloo. Dr. Satriano obtained his PhD from the University of Berkeley in 2010 and boasts a whopping 25 publications since. Without further ado, I'm ready to jump right into this, so thank you for joining me today.
Yeah, thanks for having me, Logan.
So what is your field of research, and how would you describe it to a non-math person?
So I do algebraic geometry, and it's got an arithmetic flavor to it. Usually the way I try to describe this to people, especially non-math people, is it's about solutions to polynomial equations, and it's an interplay between algebra and geometry. The whole idea is to build up some kind of dictionary that you have between the algebraic world and the geometric world. And one of the advantages of doing this is that there are problems that are sometimes more difficult to try to think about them algebraically, and they become a lot easier when you think about it geometrically. One of my kind of favorite examples when dealing with this, and this is the way I usually begin the algebraic geometry course when I teach it, is to think about the problem of Pythagorean triplets, right? So this is something that you've seen for a long time. For example, I don't know, Logan, to put you on the spot, what's the first Pythagorean triplet that you think about?
3, 4, 5.
Yeah, great, right. So you know that there's a right triangle, side 3, 4, and 5, that's right. And of course you can scale that to make it 3 times 15, 4 times 15, and 5 times 15. That'll also work. So if you wanted to try to write down all the possible Pythagorean triplets, you really only care about the answer up to scalar. And what that means is that you're not really looking for positive integer solutions to this. You're really looking for rational solutions to the equation x squared plus y squared equals z squared, or x squared plus y squared equals 1 if you want to scale out by your z. And so when you're thinking about that, you're thinking about rational solutions to x squared plus y squared equals 1, which are rational points that happen to live on a circle. And so now we have this geometric idea of a circle in mind, and once you have that, there's this really cute geometric trick you can do that as soon as you know one solution to this, you actually get all the possible solutions. And it's easier if, we had a board here, but
yeah, it's really hard
to
kind of talk about math and without being able to write stuff down.
That's right.
I think that was a really good explanation. Are you familiar with the YouTuber 3 Blue 1 Brown?
Yes, yeah.
Yeah,
right.
Have you seen his video on Pythagorean triples?
No, not that one, no.
Okay, yeah, because he has a really cool animation of showing how you can kind of generate all the Pythagorean triples. And I don't remember any of the details, but I do remember thinking, wow, just the geometry of it is really surprising then.
It's probably the same thing that I would have written up. Right?
Yeah, probably. But so you work in these you said algebraic geometry with a flavor of arithmetic geometry. So this might be kind of a stupid question, but there's all sorts of these quote unquote types of geometry, right? There's differential geometry, there's arithmetic geometry. One thing I'm going to ask you about in a second is toric geometry.
Oh yeah.
And I understand that the main idea of having these separate geometries is that you're using different tools to study these geometric objects. But what I'm interested in are what are some of the problems that are specific to, say, algebraic geometry that you can't really answer in a nice way using differential geometry or arithmetic geometry or toric geometry? Yeah,
so that's a good question. Let me think for a sec. So, toric geometry, for example, is a kind of algebraic geometry. So it's algebraic geometry involving special kind of varieties, and usually the tools that you'll use to answer those are combinatorial kind of tools of some sort. But there are definitely things, for example, in differential geometry that you can't do using algebraic geometry, or if you wanted to do it, you're saying it in a different language. One thing that you can do in differential geometry would be you put metrics on your spaces.
Sure.
And metrics are kind of inherently real or complex things that you're thinking about. And algebraic geometry, by and large, if you're doing something in algebraic geometry, it works regardless of the field that you're dealing with. So if you're going to prove something, it should roughly work whether you're dealing with like the rationals or the reals or the complex, now you've, or finite field sometimes, and so you've lost this metric, this tool that you'll deal with. So it's a trade-off. Sometimes you lose some tools, but you gain in generality the kinds of results that you can prove there.
Okay.
So definitely there are tools that are specific to the kind of geometry that you're dealing with.
Well, so right now I'm taking a course on manifolds, so in the realm of differential geometry. And one thing that I've kind of been looking at on my own that I don't really understand all that much yet are p-adic manifolds, which you can kind of still, like it's this weird kind of field, the p-adic numbers, but you can put these metrics and smooth structures on them still. So is there a field where you really can't put a smooth structure on it in order to talk about it in a differential geometry light? Or
so I don't know about that, but the kind of thing that you're talking about right now is definitely this analog. It's in what algebraic geometry and what we would call analytification, and there are many ways that you can analytify things. So you can take a variety and you can analytify it to get something that's a complex manifold, or you can analytify it to get a p-adic manifold in the way that you're talking about. And one thing that would be one of the things that you would like to do, at least in algebraic geometry, is to put all of these things on a uniform footing. That there's an analytification functor, and you want to try to draw analogies as much as you possibly can between these different settings.
Okay. And so I just want to go back to this toric geometry again a little bit. So you said that you're using more combinatorial tools for studying it, right? That's
That's one of the tools that
Sure.
I mean, there are also general tools, but
Yeah.
combinatorial ones will certainly come up a lot.
Okay. So can you give a little bit more detail about like what kinds of things that toric geometry is most useful for looking at? Like why?
Yeah. So toric varieties.
And actually, sorry, just before you continue here, could you just give like kind of a brief description of what a variety actually is? I don't think a lot of our undergrads.
Sure. So a variety is really, you're thinking of it as solutions to polynomial equations.
Okay.
And you want to, let's just keep it at that. Let's just say it's solutions to polynomial equations. Right?
Okay.
So you choose those equations. I'm happy to work over the complex numbers. You choose a list of equations. We're looking at those solutions. So yeah, that's basically what a variety is. And toric varieties are ones where there's a large piece of that variety that we already understand. So it's a group. It's a torus itself, which is why they're called toric varieties.
That's what I figured.
Yeah, and the way that you try to understand this toric variety as much as you can is, so inside of a torus you have lots of nice lines that go through those. And you stand at a line and you kind of look from the perspective of that line and you say, if I take the closure of this line, if I follow it all the way to infinity, what points do I hit as you do that? And you group your points together into clusters. Cones is what they are.
Okay.
Depending upon what kind of points that you hit in the limit as you move off, and this gives you a way of getting from these special kinds of varieties, these toric varieties, and it's a one-to-one correspondence between this and these combinatorial objects, which are collections of cones that are called fans. So,
okay.
And so it comes down, a lot of times it comes down to lattice theory kind of computations that you're doing.
Okay. So what are some of the big open problems in your field right now?
One of the things in algebraic geometry is it's a huge field, and so I mean it has connections to arithmetic things. There's complex analytic geometry, differential geometry, topology, dynamics. I mean, so many different things. So the kinds of questions that someone would list as big and open and exciting are going to vary a lot depending upon upon who you're talking to.
Is there anything kind of specific to your kind of sub area of what you study?
There are a lot. Unfortunately, I tend to not be able to think too much beyond whatever it was I was thinking about, like the last 2 days, right? So
yeah, no.
So things that are fresh in my mind, for example, are certain kinds of arithmetic and dynamical kind of problems. Those are at least the first ones that are coming to mind at the moment. So these kinds of questions are about, you have a variety, and you're working over, let's say, a number field, and here you have a map on this variety, and you're iterating this map. You started with a point that someone handed you, and you iterate this point a whole bunch of times, and you want to know what's happening as I look at the orbit of this point. And there are various conjectures about, so if you're thinking of these things as solutions to polynomial equations, right? So we have a bunch of variables that you started off with, and you can talk about what values are those variables taking. And you can ask kind of how big are the fractions. So maybe these are rational numbers, and you write down the rational numbers, and you look at so you have a over b, put it into least common terms, and you look at things like how big are a and how big are b. And this is what we call a height function. It's a way of assigning how big this particular number is. And there are various conjectures that have to do with the growth rate that you would expect for the a's and the b's that are showing up as you iterate your point many times.
Wow, that's really cool, because like, just to think, because that sounds very number theory-y, like you're looking at these fractions and you want to see, because just back to p-adic numbers, from what little I understand of them, when you're talking about the size of a p-adic number, you're looking at these ratios of and multiplied by some power of some prime number, right?
Mm-hmm.
And to determine how big a p-adic number is, you look at something like how big the denominator is relative to the numerator,
Sure.
or something like that. And then just to put that into like a geometric perspective.
That's right.
That's really
a lot of what's going on over the number field is given by the kind of p-adic metric that you're talking about, taken over all possible primes. And those are cobbled together into this thing called the height function. And a lot of conjectures deal with things of the form, the height should be controlled by, if you take a nice enough point, one that kind of moves around enough throughout your variety, because if it's trapped in a small piece of the variety, it's not quote-unquote seeing the entire variety, it's only seeing a small piece of it.
Sure.
But if you choose a general enough point, there are a lot of conjectures that say the growth rate of this height is completely controlled by the geometry. And one of, just to mention a few buzzwords, one of them is what you would say the arithmetic degree, which is roughly a growth rate of the height, is controlled by this thing called the dynamical degree, and the dynamical degree is sort of a geometric form of growth rate. So it's an equality between an arithmetic and geometric object. And there are a lot of conjectures along these lines.
Cool. So, kind of in a different, moving along for a different kind of question, why should somebody study your field in particular? Can you sell it to the undergrads who are thinking about what they might want to research for their in graduate school?
One thing that I like a lot about algebraic geometry, well, first of all, I feel I shouldn't particularly, I think if you're interested in something, if you love, if you love applied math, I'm not going to try to convince you to do, algebraic geometry. I think you should pursue whatever you particularly like, and that, because you're going to be best in whatever it is that appeals to you, right? Usually. But if you're on the fence about arithmetic geometry or algebraic geometry versus another field, one thing that I like a lot about algebraic geometry is what I had mentioned earlier, that it appeals to so many different fields. A lot, for example, in the first course in algebraic geometry, and it'll vary a little bit depending upon who's teaching it, but at least when I teach it, the focus is primarily on varieties. You're working over a field, usually algebraically closed field. But one of the points that I love a lot, and I end class with a lecture or two on these things called the Weil conjectures, which are saying that there's this wonderful connection between some of the things that you've seen over, say, the complex numbers that would be going on throughout the entire course, and information that's controlled by analogous questions over finite fields, and the inspiration for this. So these things can be stated. You can state the Weil conjectures without knowing any of the background that goes into it, but it's all about the inspiration that went into it, and the inspiration came from cohomology theories in topology, and the idea was what should be the analogous cohomology theory in algebraic geometry. And it's one of the most wonderful things to see that you get this connection. It's just inspiration. That's all it is, and then a lot of work went into making this inspiration precise. But it's so much fun to see in algebraic geometry how this one field connects with so many different things. You can prove something in the realm of algebraic geometry, and by doing this, you've simultaneously proved it for, say, complex numbers and finite fields at the same time. Or to give maybe one extremely concrete example, is there's this analogy that people say throughout. If you studied number theory, sometimes there'll be various hard conjectures in number theory, and a lot of times people will first get some feeling about whether these conjectures are true by proving them. Rather than proving them for number fields, you prove them for something called a function field. So it's an analogous field, but it's a completely different setting, and algebraic geometry, quote-unquote, explains why number fields and function fields are analogous. Both of them are fields associated to quote-unquote curves. One of them is literally a curve that you would think of from complex geometry, and the other one is z, the integers, which, when viewed appropriately, is a curve. It's an algebraic geometric curve. And algebraic geometry makes this precise about how you should be thinking of z as a curve. And it's, again, just one of those things, which it's just a change of perspective, but by doing that, it opens the door to building a lot of analogies.
Sure, yeah. So when did you decide that mathematics was kind of like the career path that you wanted to follow?
I'm not sure there was a particular moment, and it's definitely been long enough ago that I don't completely remember. But I do remember liking math for a long time. Both my parents were high school math teachers, so I guess it grew on me at that point. But I think throughout high school, I wasn't completely sure what you actually did with math. I just knew that I liked it. And so initially, I just figured I would be an engineer, and I didn't know there was this career path where you can get paid to do something which is pure math. And once I kind of realized that at some point, I thought that was a great path for me. But I do remember, for example, even as a kid, I liked doing, my brother as well, we liked doing a lot of puzzle games. I don't claim that I was very good at them, I just liked them, right? I mean, one thing actually, and if you ever get my brother talking about a kind of topic like this, he'll always go off about this one game it's a Nintendo game that we played as a kid. It's called Lolo, which, it was a wonderful game. Lolo 3. Lolo 1 and Lolo 2 are so-so, but Lolo 3, if you can ever get your hands on that. It's this... It feels a bit mathematical in the sense that you start from level 1 and they introduce you to these various little characters, and you're trying to solve various puzzles and things. And gradually you get introduced, this character does this such and such a thing, and when I see this character in this particular environment, I know these are kind of the steps I should be doing to get around, this guy I need to get around. and it's a little bit mathematical. You get introduced to these abstract concepts little by little until you get the feel, like in groups. The first time that you see a group, it might be very abstract or vector space, and then after a while, someone can just say vector space, and you know a million things that you can do with vector spaces without thinking about them, right?
Yeah, actually, that brings up an interesting question, where I can't speak for everyone in the undergrad, but I found personally that so far first year was the hardest year for me, because I had no idea. Like, I would look at a math 145 problem, and I would have no idea how to even approach it. But over the past couple of years, I think I've gotten more of a tool set to be able to, at least if I don't know what direct path to take, I know what kind of steps I can do to kind of shed some light on it at the very least. So I'm wondering, as you continue on and on to get to like the frontiers of mathematics and research, do you find that even when you're faced with a problem that you don't immediately see what the solution will look like, and it's just a matter of filling in the details, do you ever find, I have no idea how to even start this?
Or? Oh yeah, there are definitely a lot. but I do agree with what you said, though. Certainly for me as well, my first year of college was a little bit of a shock, right? I mean, because. And I think this is true for a lot of people, right? A lot of the undergrads you would find, say, at Waterloo or where I went to undergrad, etc. A lot of them are very good at what they do, and then you're introduced to a bunch of people who are all very good at what they do, and there's but there's also a huge change in mindset between high school and college, and sometimes there isn't a good way to make that mindset except a change of mindset except abruptly, right? You're in your first year of college, and I would say that from what I understand by talking with undergrads as well, I think the thing that you're talking about would be if you've taken 145, for example, and probably people who take 135 have a similar kind of shock, but perhaps it's when you make the jump, say, like if you did 135, 235, and then you go to 347, that could be a bit of a jump as well, right? Because it is a big jump in abstraction from 235 to, say, to 347. Whereas maybe if you had done 145, that was your big shock, and maybe 347 wasn't as much of a shock after that, right? Well, I don't know. You can tell me what you think about that. But,
well, for me personally, and for people who don't go to the University of Waterloo listening to this, 145 is just algebra course. 245 is linear algebra, and 347 is group theory. So for me, the biggest jump was to algebra 145. I found 245 was very challenging, but I think that I had a Ross Willard for 146, and I think he set us up really well to be able to handle math 245. And then for 347, I will admit that it's a full another layer of abstraction.
Gotcha.
And it's taking a while to kind of solidify all of these concepts, especially because with group theory, I think even you've mentioned this in lecture a couple of times. It starts out with just definition after definition after definition, because we don't really have the tools to talk about groups without them, and we haven't seen anything like that before. So
gotcha.
I think that's 347 for me at least has been a bit of a jump, but not necessarily as big as one from high school math to algebra and math 145. But that does bring up an interesting point, because you said first year of college is when you really get that shock. Do you think that there's room to change high school math curriculum around to have it more not proof based, but less just plug and chug computation? Do you think, or do you like the way it is?
I think there's definitely a need for plug and chug kind of thing. The problem is it really depends on what you're going to do in life later, right? And I'm not sure introducing a lot of abstraction is necessary if you're going to be doing a career path that isn't
Of course.
going to involve, right?
Yeah.
But for example, well, I mean, for example, my wife always finds it very funny when she's much faster at computing tips than I am.
Yeah.
Right? So she's certainly mastered certain algorithms better than I have, right? Or, but there's a need for both of these, right? The abstraction and the mastering an algorithm. Certainly being able to compute tips, maybe not necessarily immediately or very quickly, but knowing how to do it. Or you want to balance your checkbook. These are all kinds of things that it's really, or adding two numbers, right? That's just an algorithm that we've gotten extremely comfortable with, so we can do it somewhat quickly, right?
But during your undergrad, were you always drawn towards more algebra, or was there a point in time where you thought you'd go more towards like the analysis, a nice smooth structure kind of side of math?
Not so much for me. Yeah, I was more interested in number theory to begin with.
Okay.
I had done this program. It was a wonderful program called the Ross program. It was my last year of high school, which was actually a bit late for a lot of people there. Go earlier, and it's a program that's been going on for many years. I don't remember the actual number, but a few decades at least. And so it's at Columbus, Ohio. It's a summer program, and the idea there is that you learn number theory through a series of problem sets, and you have no number theory textbooks. You are not supposed to access the internet and be able to find solutions there. So you're essentially reproducing an elementary number theory course through a series of problem sets, and they go quite far. I mean, they get to quadratic reciprocity. They talk a little bit about the p-adics, not too much, but just a teeny bit. That was fun. That was a lot of fun, and you get introduced to a lot of new topics there. So I had this number theory bent, and then got into the geometry a little bit later, and kind of linked them back up again.
Yeah, I actually personally I thought I would really like analytic number theory, because I think my first big introduction to math was learning about the Riemann hypothesis. I was like, oh yeah, I'll solve that one day. But I went to a seminar from the CMS here on analytic number theory. I think it was last winter term. And what I found was that it seems to be like a lot of proving like growth bounds and like big O of this. Like there's a good joke. What does a drowning number theory sound like? Log. So and that kind of turned me off of number theory, at least for now. So now I'm kind of like in between what I wanna do. So I don't know yet, but.
Although I will say that I in analytic number theory, I remember a friend of mine gave a series of lectures on this, and the goal was to prove the prime number theorem by it was an intense week, right? Where the goal was to prove the prime number theorem by the end of the week. That was a lot of fun, right? And it was something where I didn't think I could spend my life doing that, but it was wonderful to see how they ended up going about this, right?
Well, the thing is that the problems are so interesting, like twin prime conjecture, Riemann hypotheses. Right. These are really interesting problems, but the methods that are being used to do them, I personally just don't find them compelling enough to want to study them on my own.
Right,
I think, but like the results and the actual problems are absolutely fascinating to me. So. I don't know yet. Maybe I'll flip flop back and forth throughout the rest of my undergrad, and I'll probably settle somewhere later on down the road. But we'll see.
I don't think you have to particularly decide at the moment.
Exactly.
Right? I think keep your mind open, and I mean now's the time where you can learn a lot of different things.
Yeah, my philosophy is for now during the undergrad, do as much math as you can from all the different approaches, even if you don't like it right away, because then once you get on to, so I think. No matter what field you're in, I think you'd be able to find something interesting about it, because math is just so all-encompassing of like there's something in it for everyone, no matter what field you're in. So during your undergrad, I think it's a chance to take advantage of the fact that you have all these different courses from all these fields that you can take, and then once you get to graduate school, then you can start to narrow in.
I will say, I mean, when I was an undergrad as well, that kind of philosophy, which I had the same philosophy, didn't apply just within math, but I love taking philosophy courses or literature courses. 'Cause where else are you going to have the time to do something like that?
Yeah.
I mean, of course, I do fun reading now, but I don't have the same amount of time to set aside,
of course,
and deeply think about these works.
Yeah, no, that's definitely a good philosophy to have, I think. But so from I don't know how we got off on that big long tangent, but from because you didn't actually start like straight out of your PhD. You didn't just start in teaching in academia and research, right? Because from 2014 to 2015, you were at John Hopkins University as a modeler in oncology and biostats, right?
Yeah.
So what was that like, and what kind of pushed you towards going back into academia afterwards?
Well, so that was, honestly, that was a lot of fun. It was an extremely different kind of experience. I learned a lot of statistics, which was great. I mean, I loved it, right? I mean, it was because you got to, a lot of it is linear algebra, right? And well, at least the kinds of things I was seeing.
Sure,
right?
yeah.
Linear algebra, right? And a lot more as well. But I mean, but a lot of things could be phrased in linear algebraic language, which I like. This was just a very different thing. I have interest in kind of math bio and something that one of the things I love about math is how versatile a tool it is, right? I mean, it's not it's so useful because it makes good predictions about things, right? And that's so a lot of fields are start to mathematize because it, as anybody can see when they take 135 or 145, you can have an idea of what an argument is to demonstrate something's true, but it's very different after you have to set down the hypotheses very precisely, set down your steps very precisely about how you get from the hypotheses to the conclusion. For example, I mean, I remember reading an article when I was doing the math bio stuff, where there was a guess. I don't remember the details at this point. I don't even remember particularly what it applied to, but I remember the broad brushstrokes that that someone had gotten. It wasn't even at Hopkins. It was just an article that I had read. Someone had gotten very excited because they thought that A had implied B, and there was evidence about A implying B. But then someone kind of set up, a small math model that demonstrated that C also implied B, and C was kind of just due to random effects that implied B as well, and so there wasn't much evidence. When you set it up like that and you got very similar conclusions using very different hypotheses, all of a sudden the idea that this important implication of A implies B didn't hold as much water. And it was just a matter of setting up your hypotheses correctly, choosing a clever math model that was going to end up getting the same conclusion, right? And I like that. Math allows you to make things precise. And
sure, yeah. Okay. So what was the first original mathematical result you remember producing, even if it wasn't like publishable?
Yeah, so this one that I remember definitely wasn't publishable because it was known already, but just wasn't known to me. And this was before the days where you could just quickly Google for things, and I don't think Google was the typical homepage at this point anyway.
Oh, really?
I mean, maybe maybe I had used Yahoo, but it was really like very, very early days, and going
Sure.
to the internet and having Math Overflow or Math Stack Exchange or something like this just wasn't a thing, right, at that time. But I had remembered working out. It's a question that actually I find kind of cute now, which is, all right, so let's look at the number 1/7, right, and look at the decimal expansion. And you have a computer. I don't remember what the decimal expansion is, but you can see it quickly.
Sure, yeah. Calculator, okay, 1/7. 0.142857142857.
Okay, great. So it has length 6 before it repeats.
Sure.
Okay. And so I was just playing around and looking at 1/n and looking at what the maximum length that you would get before it starts to repeat. And so let's just concentrate on 1/7. So 1/7, I mean, why look base 10? I mean, base 10 is completely arbitrary. So,
Sure,
so
yeah.
don't look base 10. You can look various bases, and you can ask, when is it going to have length 6? So if you just play around in various different bases, you see the length 6 is the maximum that you're going to end up getting.
Okay.
And you can play around in different bases, and you can ask which base B are you going to have length 6 as the repeating length that you're going to get. Of course, sometimes it could be like if you look base 7, it's just 0.1. So it does repeat, it's just 0.1000000. But let's rule those out. Let's talk about the ones that are just periodic and length 6. And I just started to notice some patterns about what was going on. Now, basically I come up with a formula for what the max that you would ever see of 1/n. And so look at the fraction 1/n, look at various bases b, and see when that's going to be periodic and what the maximum length that could be. And it took me a while, but eventually I worked out what a formula was for this. And what I had no idea until much later, that I had worked out a formula for Euler's phi function of what n was.
Okay.
And this is basically, I mean, once you know a little bit of number theory, you see that this is the fact that 1/7 has length 6 as its repeating thing is the fact that 10 mod 7 is an element of order 6. And so, I didn't have the language, I didn't know those tools at the time, and so, you were working out. Yeah, so it was a lot of fun, I started to notice these patterns, and I was like, how do you prove this? And I had some long, very, very convoluted proof that eventually led to this, but I mean, it took a long time, and of course, because, well, like I said, I didn't have the tools.
So when would this have been then, in like your undergrad or?
No, this was maybe my junior year of high school, something like that.
Oh wow, okay, so you were always doing math then.
Yeah, well, again, it was just playing around. It was fun and stuff like that. And then it was after I went to the Ross program the year afterwards, and I learned about all these things about generators of Z mod P star and things like this, that I realized, oh wow, this looks really familiar. The phi function has this formula. That was the same formula I got. And then of course, once I realized it was the same formula, then it was pretty quick to see the connection. I just hadn't seen that connection before.
Okay. So now something that was published, your PhD thesis, which was titled On Stacky Resolutions of Singular Schemes. Could you talk a little bit about what it was like writing a PhD thesis, and how does a PhD defense, what does that look like?
So for that, I'm not a good person to talk to. So Berkeley doesn't have PhD defenses.
Oh,
actually.
really?
It's the writing of the thesis, and the advisor and the committee give it a good vetting, and that's it. So.
Have you ever supervised PhD defense?
I've been external members to PhD. I have one PhD student right now, but he hasn't, he's still working.
Still a ways out?
That's
yeah,
right.
Sure. So, what can you talk a little bit about the process of writing a PhD thesis?
Oh, sure.
It's kind of like the first kind of thing that you present to the mathematical community most of the time, right? Like,
right.
That's a lot of the time the first thing people will publish.
Right.
So, what is that like, and how does it get easier over time?
Yeah, although I will say that it feels like the game is changing. There are so many bright grad students
Oh
who
yeah,
have
that's true.
lots of applications before their PhD. Um, but what's that like? It was for me the experience will probably vary a lot depending upon who you're talking to, but the actual writing of the thesis wasn't that hard for me. It was all the work that went before that, right? But in my case, I had kind of had 3 papers already, and
Okay.
I mean they weren't published by then, but and so it was the so all the work had gone into those 3 papers, and it was taking those ideas, and there was already a coherent story flowing throughout them, but it was throwing in the background, making sure that there was enough exposition and enough connections between these. But I felt for me most of the stress was before the actual writing of the thesis.
Okay. Sure. Now, once you get to that kind of level of research, how hard is it to find sources? Because in my experience, I was lucky enough to be able to audit PMath 940 with Dr. Rubenstein, and one of the kind of things, like the only assignment of the course was to present a lecture on something that we didn't have time to cover in the course. So me and the other student that I was auditing it with chose to do the Selberg integral, and we couldn't really find almost anything kind of details of how you build this integral online. So it was the first time I actually had to go to the library for something. So I'm just wondering, once you get to kind of your level of research math, how frequently do you actually have to go and find paper sources, or is most of it online now?
I find most of what I want is online, but it's because the universities have good journal access, right? So,
Sure,
so
yeah.
I'm finding the same thing that you would find in the library. I can just find it on my computer instead. I rely on published material all the time because it's always this mix. You want to do original things, but you want to build upon what's already been done before, and you don't
Sure.
want to be doing math in a vacuum because, it takes too long to build up math from scratch anyway, and is always disappointing if you spend a lot of time doing something and then you discover that it's been done already. So, so you want to maximize the knowledge of what's actually out there so that you can do new things
Sure.
that you find exciting and building upon past things.
And there's another question in there for you. Just the rate at which math papers are being published now is like insane. So how do you stay on top of it to make sure that what you're working on isn't something that Joe Blow from some other university is like days away from publishing?
Yeah, I remember when I started doing math research, my dad had asked me something like this. Was like, don't you guys end up proving the same things all the time as somebody else? And I was kind of surprised to see that at least for me personally, that it hasn't happened that often. It did happen once before, where there was a result that I was excited about, and then actually 2 papers within 2 days of each other had gotten on the archive, proving the thing that I was interested in. But they were maybe at least 6 months of work ahead of me, right? So,
Yeah.
So I mean, I didn't have a chance at doing that. Of course, I had already put in about 6 months of work into it.
So
but,
that's got to be a big
yeah.
kick in the shins. But because I've talked to, Professor Forrest, his field, like, it's a very niche field. There aren't very many people working in it. So I feel like that's not going to be so big of a problem when there's like a couple of dozen people in the entire world who understand what you're working on. But in like geometry, I think geometry is probably the most popular subfield of math, just because it's got it's more intuitive. So if I'm less talented at like algebra and this abstraction, I can kind of have an intuitive hunch for why this is going to be, because I can kind of visualize it in some sense in certain circumstances. But so whenever you have all these people working on the same kind of subfield, I'd feel like there would be more clashes more often between mathematicians who are working on the same thing.
Yeah, it's possible. But then again, if you have a field where it connects with so many other things, there are a lot more problems, right? That you can connect.
Yeah, of course.
Of course, there are always these I can't think of the holy grails, right? That probably a bunch of people are interested in. Of course, those are a lot harder to prove, right?
Yeah, of course.
It's a mix.
Sure. So, is there anything exciting going on in your field right now? Like, was there any big recent publications that have kind of shed light on perhaps we're going to be able to answer this problem that has been plaguing the geometry community for a really long time? Or?
One thing that happened, I believe it was in July, that was, so it's a paper by Lawrence and Venkatesh, so the result is, so they have a reproof of an older result by Faltings, and it's different techniques, and so the idea is people are excited that this might, it's a new way of looking at it, and the hope is that this might shed light on more general cases of this. So I mean, Falting's theorem is, I guess, to link it back to the circle, right? So when we talked about x squared plus y squared equals 1, and there are, well, lots and lots, turns out there are infinitely many Pythagorean triplets. And when I say infinitely many, I mean where divide out by scaling, right? So 3, 4, 5 is the same as 6, 8, 10, right?
Yeah.
To consider those the same. And so x squared plus y squared equals 1, you're looking at, there are infinitely many rational solutions to this. And so the circle is an example of something that you would call a genus zero curve, and one of the most basic invariants of a curve. Yeah, so one of the most basic invariants that you'd have of a curve is its genus, which from the topology point of view. So a curve in algebraic geometry is the same thing as a Riemann surface. So you kind of imagine it as a bunch of donuts that are stuck one to the other.
Sure,
like
yeah.
A bunch of donuts, and you're counting up the number of holes that are inside of them. And the genus is the number of holes that you count up. And so what Falting's theorem says is that if I give you a curve, and let's say it's cut out, right? So a variety is cut out by polynomial equations. Suppose that these polynomial equations all have rational number coefficients. And if the genus is big enough, so at least 2, then there are only finitely many solutions to this, finitely many rational solutions to this, which is very different from the circle where there are infinitely many solutions. In fact, on the circle, as soon as you have one solution, you have tons of solutions. It's also very different from the genus 1 case. Genus 1 curves are also known as elliptic curves.
Okay.
And there, you can end up with infinitely many solutions to this. And there's this contrast when you move to higher genus.
Okay.
And it's because you had mentioned about differential geometry. The way a differential geometer thinks about this is, the way an algebraic geometer thinks about it is there's this trichotomy where you have genus 0, 1, and higher genus.
Okay.
And a differential geometer thinks of this between positively 0 and negatively curved spaces. And that's the kind of trichotomy that shows up.
Okay. Yeah. So if a genus 1 curve is an elliptic curve, I kind of know the general form of the actual equation you'd write out an elliptic curve. Is there an analogous one for, like, say, a genus 2 curve or a genus 3 curve? Like, how would you actually write those out?
That's an awesome question. So actually, this links to a theorem that I really like, which is, okay, I mean, I'll lie a little bit, but basically here's the statement, which is, suppose I say I'm going to give you a genus 24 curve, or, well, let's even make it bigger,
sure.
Whatever it is, like genus 20, 30 curve, whatever it is, and you ask, what's the general form? Like you just told me that for an elliptic curve, you know how to, as long as you're avoiding like certain characteristics, you can write this down as y squared equals x cubed plus ax plus b. Right?
Sure, yeah.
That's the way that it looks. You can ask, what's the general form for a genus 24 curve? And it turns out it's impossible to write down.
No way.
Which is really cool. So any kind of equation that you're going to write down that you think captures all genus 24 curves, it turns out it only captures a very small subset of what those genus 24 curves actually are.
So do you get like a class of equations then that you can study like certain subset of the genus 24 curves, and then maybe you want to look at this other set of equations that describe some other smaller set of...
That's right. And so so one of the first ones that usually would come up in an algebraic geometry course is something called hyperelliptic curves, which are kind of they also have this form y squared equals something involving x's, right? And they're hyperelliptic because, well, they what you know, like you would say, it kind of looks like the equation of an elliptic curve to begin with.
Sure.
But yeah, this is this wonderful theorem, and it actually also links back to this problem that I guess I had talked about earlier, of how geometry controls. Well, in this case, it's not really arithmetic, but this trichotomy that we talked about of genus, that higher genus curves behave differently in some particular way, and this is this wonderful. Actually, let me talk about this one thing. I feel like I should throw this in because now that I'm talking about this, you asked me what's a technique that shows up in algebraic geometry that you wouldn't see in other fields, and didn't occur to me at the time until now that we're talking about it. But this one technique, which is really throughout algebraic geometry, it's a wonderful technique, which is, suppose you're interested in genus 24 curves. You could say, let's write down the set of all possible genus 24 curves. And there's a way of taking that set and turning it into a variety itself. So the set of genus 24 curves is a variety. Again, I'm lying a little bit, but it's basically true. And it's actually something called a stack, which is what's going on in my thesis. But so the set of genus 24 curves is a variety. And that's something that comes out, it's a technique throughout algebraic geometry. Suppose you're interested in a particular family of objects. Can you fit them together into a variety itself and then study that variety? Like if you're interested in things like how many, suppose you're looking at projective space, like P2 or something like this, and you want to know if I give you a degree 15 curve, how many degree 15 curves are going to go through 25 points. I write down 25 general points, and you want to know how many degree 15 curves. Anyway, so these kinds of problems, if I give you degree D curve and it has to go through n points, it's related to this field called Gromov-Witten theory, and a lot of the techniques involve you write down the space of all possible degree D curves. That's a variety. You study that variety, and you start to prove properties about it.
That's crazy. Wow.
And that's very different from, say, if you're studying the set of all n-dimensional manifolds. That's well, anyway, it's just it's a different game.
For sure, absolutely, very cool. So, what's your most proud mathematical achievement?
There are some results that I've proved that I think are kind of cute. Maybe. So maybe one. Let me say one result that I'm working on now, rather than talking about my most proud achievement. Well, okay. Maybe a quick one or two sentence thing about something that a cute result that I like that I showed, which is that there are certain kind of spaces, they're called stacks, and stacks kind of also fall into two kinds of categories. They're kind of the more tame ones called Deligne-Mumford stacks, and then the slightly more unwieldy ones called Artin stacks. And the Deligne-Mumford ones, there's a nice way of talking about things like in this stack just think of it like a variety, whatever it is, and I give you some sub-variety, and I give you another sub-variety, and you want to talk about how do they intersect. And there's this nice theory called intersection theory that exists on Deligne-Mumford stacks, and there were a few people who were interested in things about to what extent does an intersection theory exist on Artin stacks. And there was essentially a two-step plan that I had with Anton Gerashenko and Dan Edidin that we wanted to do in order to get this theory to work out. And the first step was to show that essentially you can integrate on these more unwieldy stacks. And what we ended up showing instead is that it's impossible to form a degree an intersection theory on Artin stacks. So we had ended up axiomatizing what an intersection theory, the most basic properties that you would ever want to exist for an intersection theory on these Artin stacks. And then, we fully expected that we were going to be able to write down some definition. We had many candidate definitions in mind, but they kept running into problems. And then we were like, well, why don't we just axiomatize what this is, and so that we can figure out where this problem is actually living, which axiom is this thing going wrong in. And then we just ended up showing that it's impossible, to do this, which, that there are other ways that one can think to get around this problem. But that was one result I thought was kind of cute, also because it grew out of this other theory that Anton and I had developed, a theory of toric stacks. But maybe I can just mention a couple of words on this one thing, because it also something that I'm thinking about right now with David Zurich Brown and Jordan Ellenberg. So maybe you've heard of Jordan Ellenberg has a lot of popular math books. One of his most recent one, which I was transiting in Chicago, and I saw it in the airport there, which was it's called How Not to Be Wrong.
Okay.
Yeah, it's anyway. You should check it out if you haven't. So this is a problem that we call it the Stacky Batman conjecture, because one of them had realized that, I forget which of the two had realized that there was this other conjecture called the Batarev-Monin conjecture, and if you take Batarev and Monin and you take their first few names, you get the Batman conjecture. And so we were so there are these kind of two conjectures. Again, it's a geometric versus arithmetic thing. So there's this Batarev-Monin conjecture is something about so Falting's theorem, right, says that for genus 2 or higher curves, you only get finitely many solutions, rational solutions, right, to this thing. And so there are other kinds of conjectures that have to deal with not just curves, but higher dimensional varieties. And there are various conjectures. So if you're in the situation where you are getting infinitely many things, like higher dimensional analogs of the circle, you can ask, so just like going to an analytic kind of question, great, so there are infinitely many. That's your first step. The second step is now how many? Well, you already said it's infinite, but so that's not a good answer. You want to know, order them in some reasonable way and talk about the growth rate of that. And then there are very precise predictions about what the growth rate should be, which again, that's an arithmetic thing because you're counting rational solutions to this. But the growth rate is predicted by the geometry of this again, and it involves logs, so you have that. So that's on the kind of geometric side, where you're counting rational solutions to these geometric things. And then there's a completely different thing, which is kind of played a role in this Manchol-Bhargava style stuff, right? Where you're counting number fields. And there's some way of ordering these based on their discriminants. And you can ask, how many number fields are there with kind of a given Galois group, and you want to order them by discriminant, and then you look at the growth rate as you allow the bound to go to infinity. And again, there are precise predictions about what this is called the Mala conjecture, and it again involves log terms and some linear terms, or powers in linear and log terms. And these two conjectures just look so similar that you're like, what's going on? So you can ask the question of, are they the same conjecture? And what does that even mean? Because they're taking place in different areas. And so the goal of this thing, which it's almost finished, this project that we're working on, is we realize that instead, if you develop a theory of heights on stacks, and we have conjectures. This is our conjecture, the Stacky-Batman conjecture, which is predicting. So first we had to develop a theory of heights on stacks. There were some that existed, but they weren't really doing what we wanted them to do. So we had to soup that up. And then we have precise prediction, conjecture about what the growth rate of these things should be. And then when we say our stack happens to be a variety, we get the usual batter of Monin conjecture. And when our stack happens to be a very special stack called the classifying stack, which BG, if some of your listeners know or more topologically inclined, that's where this comes up. Then you end up getting the Mala conjecture. So the Stacky-Batman conjecture actually it incorporates, it interpolates between these two conjectures. Now it's still a conjecture, but we developed this theory of heights, and it at least puts these two similar sounding conjectures, which were initially distinct, and it puts them on the same footing.
That sounds like a pretty big deal.
Well, it's fun at least, right?
No. That sounds really important. Do you think they'll name it after you? That sounds like really important.
I don't know. Well, I mean, again, it's just a conjecture. We haven't actually.
Of course.
And we proved a few cases of it, right? But
sure.
But it's because there are so many cases where the batter of Monin conjecture and the Mala conjecture are open. It's not like we can prove the Stacky-Batman conjecture, because then we would prove both of those conjectures.
Yeah,
that'd be
a big deal.
That would be a very big deal. But
very cool. Okay, so I guess then, because the next question is, so what your most proud mathematical achievement is. Flip side to that is, what's the one problem you wish you could solve? Would it be to kind of classify, like, show that this Batman conjecture kind of solves everything, or is there something more that kind of keeps you up at night?
So there are definitely a lot of things down this path there are so many questions I would like to answer. Maybe one that's of a different flavor that I really like, and it came up during my time in Michigan. I was talking with Bill Fulton, and he had this question, which initially when he told me, and a few people have had the same reaction when I've mentioned the question to them as well. The reaction was like, "There's no way that's true," and yet couldn't find a counterexample, right? And then ended up proving some cases where this was true, and the problem is a kind of local to global problem. So there are certain varieties. They're said to have quotient singularities, which basically means that if you look locally at this variety, then it looks like a smooth variety modulo a finite group. So you can imagine a finite group acting on this variety, and you take a quotient and you get some new kind of variety.
Sure.
And what the question is suppose I give you a variety which locally is smooth mod finite group, then is it globally smooth mod finite group? And I don't know, but my initial reaction toward this is that seems very unlikely, but haven't been able to write down a counterexample. And I have a rough plan as to how I would show that this is actually true, but you know, there are a lot of steps that would be involved in that.
Well, what's that one quote that's like, the axiom of choice is obviously true, Zorn's lemma is obviously false, and who knows about the well-ordered principle? Right. Yeah, that's funny. So, do you have a favorite theorem?
Yeah, I guess again there are a lot of them. I guess I had mentioned this one of the genus 24 curves, and it's genus at least 24 curves, which I really love because it's counterintuitive. I think my quote unquote favorite theorem will vary a lot depending upon who I'm talking to. So in the sense of one that I like one of them that I like, which is a favorite theorem mainly for shock value, is the insolvability of the quintic. Because it's so simple to state, and yet to prove it, you need to know some stuff, right? Another one I like, if I'm talking with people who are non-math people, is that there are different kinds of infinities. I think this is very counterintuitive to people, that the integers and the real numbers are both infinite, but they're different infinite. And a similar one initially when you mention it to people is that they're the quote-unquote same number of even numbers as there are numbers, right? But yeah, no, there are a ton of other ones that I really like. So some of them maybe because they come up in my own research, but I definitely like this genus 24 one, for example. I know there was another. I know there was another one in the back of my mind, but it's not coming forth right now. So.
Well, I actually had a kind of similar to the different sides of infinity kind of like big mind-blowing thing recently, because one of our bonus problems for real analysis on one of the assignments was looking at in order to prove it, you needed to kind of come up with an idea of what transfinite induction is. And then just this idea of doing induction, and then you can't get all the way to the end, so you have to take the limit, and then you go on to the next infinity, and then you do the same thing, you prove it works for those, and then you take the limit. I just thought that idea was just mind-blowing to me. I didn't end up solving the bonus problem, but I kind of think I have a better appreciation for what it was actually asking. So, but that was that was interesting to me. I wonder, do you still find there are things that just kind of completely blow you out of the water? Like, I was not expecting this at all.
Oh yeah, a lot.
Yeah? Okay.
Again, I'm not sure if I can think about something off the top of my head. Presumably there was even something that happened within the last couple months, but yeah, I'm not sure I can
Sure,
think about
yeah.
one.
That's something that you've on the spot for that. So.
But it would. But this does happen to me.
Yeah. Okay. Well, that's good.
And that's always fun, right?
Yeah.
So one of my old roommates who was a mathematician as well, in Berkeley, and he would love. Well, okay, finding counterintuitive things. I love that as well, right? So I love that for the same kinds of reasons that he would love when he would get stuck on something, and I wouldn't like getting stuck on something, but I did understand his perspective in the sense that he knows he's going to get unstuck at some point, and when he gets unstuck, he will have definitely learned something, because I thought that was a pretty cool philosophy, because there's some reason why you're stuck. It's because you've arrived at a contradiction between two things that you definitely thought were true, and then when the contradiction gets resolved, you've learned something new. One of those was false, and then you get to learn why you thought that one of those was false as well.
Yeah, well, that's I like getting stuck when there's not a time limit.
That's
when there's assignments due tomorrow and it's already 3 a.m., I'm not happy that I'm stuck.
Yeah.
Do you got any math jokes?
Oh, yeah, of course there are a lot of them. Sometimes math jokes are not particularly funny, but here's one. There are of course tons of them that you've probably heard, like the how do you tell if a mathematician is extroverted if they look at your shoes when they talk to you, right? Which I think is
that one is funny.
Here's another one that maybe I feel like is lesser known. It's definitely a joke in the probably toward the analytically minded people. Which is let epsilon be less than or equal to 0. Anyway, again, it's pretty stupid.
Yeah.
But it's like, why would you have to say that, right? Or like, let p be a prime. When is p anything other than a prime, right? To the number theory people. But
yeah, that's true.
There are various jokes surrounding more in algebraic geometry about the idea. So there's this basic operation called a blow-up, and basically. It's called a blow up because it kind of takes a point and it puffs, quote unquote, puffs it up with air, and so it blows up into a much bigger thing blows up into a little sphere instead of just a point. And so there are various jokes that you can find on Math Overflow surrounding the idea of if you're studying two-dimensional objects and you're talking about blowing up points on the plane and, like things in airports and whatnot.
Okay.
But anyway, maybe I won't try my hand at any of these particular jokes.
Sure, fair enough. Do you have any mathematical heroes or favorite stories from math history?
I feel probably my math heroes are more. I'm not sure I have a math hero who would be out of the ordinary from most of the.
Of course. I mean, everybody's like
Euler.
Exactly.
But maybe not about heroes, but about a story that I like is this meeting between Montgomery and Dyson. Montgomery this was at IAS and he had worked out a distribution involving, it was essentially about if you have a zero of the Riemann zeta function, how likely is it to find another zero close by, right? And he got some evidence as to what this should be, and happened to mention it to somebody else, and so Dyson had recognized this as another distribution which involves is related to random Hermitian matrices. So if your Hermitian matrices, if the entries are chosen from a Gaussian, then what's the distribution that you're going to be seeing on the eigenvalues of this?
And the eigenvalues distribute themselves around the.
It's the same kind of same kind of distribution that you end up getting, and I love that because it's this idea of keep your eyes open. You have no idea when something that you've even been thinking about 2 years ago, when that might come up. You're sitting in a talk and all of a sudden someone mentions something and you're like, that's the idea I've been missing in order to solve this particular problem that I was working on. And not only within your own field, but things that are different fields as well. So I like that story just about, especially because it talks about the need between interacting with people outside of your discipline, which I think is pretty important.
Yeah. Well, you're giving me flashbacks there, because that was the topic for the PMath 940, looking at the unitary Hermitian matrices and the distribution of the eigenvalues, and I understood absolutely none of it. But I think I should probably go back and look at the notes that I took, because I think now that I'm in third year, I think I'd be able to have at least some better understanding of kind of what the motivation was behind what we were doing, even if I couldn't work out or understand what exactly
that's the thing as well, right? I mean, returning to old things. I always find I have new understanding or new insights into them the second time I hear it, right? That's why even if I've seen somebody give a talk once before, sometimes it's great to see them give a talk again, because it's like now you roughly know what they're going to be talking about, you know what to expect, and now you can listen for more details that you missed. Same kind of thing if if there's a movie that you really like and you watch it the second time.
You can pick out details that you missed the first time, and
foreshadowing.
It gives you more time to kind of think about why you're motivating, what's motivating why you're doing this.
Sure.
So I completely agree. So we've actually gone over time a little bit. So I've got one last question for you, which is, what advice could you give to us aspiring mathematicians who want to be doing research one day?
I think along those lines, one thing that I would say, I guess it's similar to the story that I just mentioned, which is keep your eyes open. You have no idea when something that you've learned is going to come back. But I also like this idea. I guess my advice would be curious and do things that you particularly enjoy. But allow yourself time to kind of quote unquote play around mathematically in this idea of, even if you think it's a particularly silly problem that you're thinking about, if it's fun to you and you start to work it out, you never know when it might end up coming back. I do remember when I was a grad student, there was a particular topic that I had learned where it didn't end up going anywhere after 3 months of thinking about it. And I told my advisor that, man, I feel like I wasted a lot of time doing this. He was like, it's never a waste of time. You have no idea when this is going to come back again. And it actually did come back again later on. And so I was glad I had spent those 3 months learning this. The idea of just staying curious, and that math comes in many forms, right? I mean, there's pure math, there's math bio, medical devices, there's statistics. Whatever it appeals to you, if you're mathematically inclined, take math, take the forte, take this math and bring it to another field. The human genome sequencing, for example, right? I mean, some chunk of this was setting up appropriate math models that would allow you to carry this out and make this a feasible thing. That there was, of course I'm blanking on the name right now, but there was a mathematician who moved over into that field. I think it was Eric somebody, and I can't remember the name. Anyway, yeah, had he not done that, who knows how things could have been differently. And it's always great to keep your eyes open.
Okay, great. I think that's a great piece of advice, so thank you very much. And thank you very much for coming on the show.
Yeah, it was a lot of fun. Thanks for having me.
All right.